Hey everyone, and welcome to the Transport Layer Practical Problems course. Along this course, we are going to solve multiple problems about the transport layer in networking and transport protocols. Now, it is important to bear in mind that this course is the continuation course, the previous course, which is the Introduction to Transport Layer in Networking, where we study all of the fundamental concepts and notions so we can solve all of the problems. So very important, if you haven't enrolled for this course, for the introduction course, very important that you do, and you can do it for free. In fact, in the description of this lecture, you can find a link where you can enroll for this introduction course. And once you have completed this introduction course, then you can proceed with this course where we solve multiple problems. Hey everyone, and welcome to the section on solved problems on transport protocols. On this lecture, we are going to present the first problem, the problem 1, and we are going to solve the first question of this problem, which is the question A. So, this problem 1 states, given the following partial TCP capture, this TCP trace, so we are using here the transmission control protocol between two applications entities, identified by port numbers that we see here, 3287, this is the application A, and then we have the other port, which is 2043, and this is the application B. So we can see here on this TCP trace, we have the information in the columns that we already learned. Remember on the lecture on TCP dump, we learned how to interpret and understand these traces, these captures that we see here. First, we have the time column that identifies when the packet has been sent. We have then the source column, which identifies which application sent this frame. We have the destination column, okay, that represents which application received this frame. Then we have the flags column that identifies if we have a packet that belongs to the three-way handshaking process. Remember that we have the synchronization, TCP segment. We can also have the finalization, okay, and also the acknowledgement. So this is all described in the column of flags. And finally, we have the column of sequence number and size. The sequence number is merely the sequence number of the packet that we are sending. And then what we have in parentheses is the size, which is the size of bytes of the data. So it is the size in bytes of the data that we are sending. Keep in mind that if we are not sending any data at all, if we are only sending the TCP header, then this size is going to be 0. There's no data to be sent, so this size is 0. We already saw this previously, right? Very well. So given this TCP trace, right, given this capture, we have a series of questions. Also here the problem says we have 3 unnumbered initial shipments and initial packets, and after a while the sequence of numbered shipments, so number packets from 1 to 20, with which the connection is finished. And this is precisely what we see here, right? We have this series of packets at the very beginning. Okay, it is not hard to see that this is going to be the connection establishment, the TCP connection establishment. We're going to come into this in a moment. And then we have a series of packets here. Okay, that's why we have this ellipses. We have here a while. Okay, time passes, and then we have these final 20 packets that are sent. That's why here we have after a while, because after the connection establishment, we wait a moment, we wait some time, and then we have these last 20 packets. Okay, so given this capture, given this frame, we have the series of questions, okay? On this lesson, or this lecture, since this is the first time that we see this problem 1, we are going to present all of the questions. However, we are only going to solve the first one, the question A in this lecture. So we begin with the question A. Okay, first question, does the sequence that we see correspond to any known application? Well, we need to justify if this is the case or not. Application A sends information to B, but does the application B send any information to the application A? Also, something that we need to think and justify on. Finally, how many octets does the application A send exactly? Then we continue with the question B, on which of the two machines A or B was the capture made, and also identify 3 mechanisms to find this out. And from these 3 ways of finding out which machine did the capture, which ones or which one could have been used in this problem. Then we continue with the question C. Taking into account the information available, what is the estimated round trip time, which is this RTT? What is the actual effective speed? What maximum effective speed could we achieve if the application A were to send the application B a very large file? What has to happen to be able to reach that speed? Okay, so also this is the question C. And the final questions are the questions D and E. The question D states, draw the evolution in time of the congestion window during the entire sequence, so from sequence 1 to sequence 20, indicating the phases of the slow start congestion avoidance algorithm. Remember that we already studied this algorithm, the slow start and congestion avoidance. So this question D is related to that algorithm. Finally, is there any anomaly in the evolution of the window? Well, we need to reason about that. And the final question of this problem 1, the question is states, if after sending the packet 13, okay, the frame 13, there are still 30,408 bytes to send, and there are no more losses, draw the new evolution of the real window until the start of this connection. Okay, so this is the problem 1, okay, as we have mentioned, we're going to solve only the question A in this lecture. So let's begin. The first question, okay, of this point A is, does this sequence correspond to any known application? Well, this is a very easy question, very short question, and there's a very trivial way to know if this is true or false. Remember, a known application is any application that has a port from the range from 0 until 1023. They are the so-called well-known ports. So if we analyze this sequence, we see that neither of the applications, neither the application A and the application B have a port in this range, okay. All of them, the application A and B, they have a port greater or equal to 1024. So this is false, okay. Does the sequence correspond to any known application? No. Since none of the ports are well-known ports because none of them are below 1024, right? They have what is called ephemeral ports. They are ports that are greater or equal to 1024. Okay, we continue with the question A. Application A sends information to B, but does B send anything to A? So before continuing answering this question here in the point A, first of all, let's analyze this capture. What we see at the very beginning. At the very beginning, we see the TCP establishment. This is the process of the three-way handshaking, remember? And which application begins? Well, the application that begins is the application with this port, the 3287, which is the application A. So it is the application A that begins here the communication. So let's draw a timeline so it is easier here to visualize, okay? It is the application A that begins the TCP connection, okay, and begins here the establishment of the TCP transmission. And so what is this first packet? Well, this first packet we see here, the first one, okay, that we see at the very beginning, is the packet that has the flag S. Remember that the flag S specifies the synchronization flag. Okay, we have the synchronization flag. And if you remember, this is the first step in the TCP connection establishment. Also, we can also ensure that the application A is the client and the application B is the server, because it is always the client that initiates the establishment. Remember this. In the TCP connection establishment, always the client initiates. So we know for sure that the application A is the client, if this was a question, right? So we have here the synchronization packet that we send. Then what we have in response from the application B? Well, we can see that now in the second line, this is a packet that is sent from the application B. It is the TCP segment that is sent from the application B. We know that because the source is now the port 2043, which is the port of the application B, to the destination A, which is this port. And the flags, what are the flags? Well, the flags are the synchronization and the acknowledge. The acknowledge is to confirm to the application A that the client, the application A, can send information to the application B, to the server. But we also want to be able to send information from the server to the client. That's why we also need to send the synchronization flag. And this is the second packet that we send in here, okay? From the server, from the B, okay, application, we send the acknowledge, so the acknowledge in here, and also the synchronization, both. Remember that this was the second step in the connection establishment of the three-way handshaking process in TCP. And then what we see here on the final segment, well, the final TCP segment that they send is the segment from the application A, which is the client, to the application B, which is the server, with the acknowledge, okay? And with this acknowledgement, with this confirmation from the application A to the application B, with this acknowledgement, then it is possible to send information also from the server to the client. This doesn't mean that this information will be necessarily sent, but it is a possibility, okay? We ensure that this can be done if this is needed. And so this is the third step in the three-way handshaking process, okay? With this we finish the three-way handshaking process in a TCP connection establishment. Remember that we saw all of these notions in the theoretical lectures. So now, coming again back to the question, application A sends information to B, but does application B send any information to the application A? Well, to answer this question, we need to look at the last acknowledgement that the application A sends to the application B. Because in that acknowledgement, we will have a value, and this value is going to tell us how many bytes of data, okay, were sent. And depending if these bytes of data were 0 or not, imagine that this number of bytes of data was 0, it means that we have no bytes, and in that case we will have a specific value in here, and this specific value will be 2. And now we are going to reason why. Keep in mind that if the acknowledgement here, the last acknowledgement that the A, okay, the application A sends to the application B, if this acknowledgement, the confirmation number is 2, this means that B has only sent the synchronization and the finalization, okay, to the application A, but no data at all. Remember that this synchronization and finalization that B sends to A is precisely the second step on the three-way handshaking process of the connection termination. Remember, we have a process which is the three-way handshaking process for a connection establishment, and then we have also a three-way handshaking process for the TCP connection termination. We also saw this. So as we can see, what is happening is the application B, the server, is going to be sending the finalization and the acknowledgement segment to the application A, and now we are only going to have this segment and this segment, so that the sequence number is going to be 0 bytes of data plus 1 plus 1. This gives us 2. That's why this acknowledge here is 2. The last acknowledgement from the application A to the application B is 2, and so this is precisely telling us that the application B has sent so far 0 bytes of data. It only sent the synchronization and the acknowledgement. So the answer to the question, does B send anything to A? No, because the last acknowledgement that we just discussed, that A sends to the application B, is the value 2. Okay, this means that we have 0 bytes of data. We only have the synchronization and the finalization. Remember, we will always have the synchronization and the finalization. That's why the value is 2. Okay, but what is important is that we have 0 bytes of data. So no, B doesn't send anything to the application A. Finally, this point A finishes with the question, how many octets does A send exactly? Keep in mind that when they ask for how many octets, this is the same as asking for how many bytes. An octet is a byte. Okay, there's a collection of 8 bits. So to answer this question on how many octets or how many bytes the application A has sent to the application B, it is very simple to answer, and this question is very related to the previous one. Okay, the only thing that we need to do is to study the last acknowledgement from the application B to the application A, because in this acknowledgement, this confirmation number is going to have the number of bytes that the application A has sent to B so far, plus the synchronization, okay, value, which is 1, plus the acknowledgement, with this case the finalization. So essentially what is going to have is the number of bytes of data plus the finalization and the synchronization, right? So essentially we only need to subtract this value 2, so we can have the total number of bytes of data, of real data, that the application A has sent to the application B. So we can see that the last acknowledgement, again, very important, that the application B sends to A, this confirmation, okay, as we can see, this is the port of B, this is the port of A. So what this is basically saying, and it is telling us, okay, I am B, I am confirming that I have received from A this number, okay, this confirmation number, which is this number of bytes of data, and we need to subtract 2. So how many bytes of data? Well, this value minus 2, because keep in mind that in this value, in this confirmation number, it is also included +1 of the synchronization and +1 of the finalization, right? So if we subtract this value, 20,242 minus 2, this gives us 20,240. This is the total number of bytes. This is the total number of octets of bytes that A has sent to B. So very important not only to know these values and these solutions, but to know how to reach these solutions and how to arrive to these values, how to reason, okay, the process of arriving to these solutions. So very important here, remember. Does the sequence correspond to any known application? Very easily, we just check the ports. Both are below or 1024. No, none are below 1024. Since none of them are below 1024, they are not well-known ports. They are ephemeral ports. And then on the application A, okay, sends information to B. But does B send anything to A? Well, we only need to look at the last acknowledgement, okay, from the application A. And this gives us 2. So we only have the finalization and the synchronization. We have 0 bytes of data. And here, how many bytes or octets that's A sent to B exactly? We only need to look at the last acknowledgement from B, okay, which is here, this acknowledgement in here, and we only need to look at the confirmation number, and we need to subtract 1 for the finalization and 1 for the synchronization. And so this gives us 20,240 bytes, okay, which is the number of octets that A has sent to B. Very well, so with this we finish this first question of the problem 1, the question A. On the following lecture we are going to continue to solve this problem, and we are going to solve the question B. On this lecture we are going to solve the question B of this problem 1. We already introduced and presented this problem 1. Remember that we had a TCP trace, a TCP capture, and we had a series of questions to respond and to answer given this capture, right? So this lecture we are going to solve the question B. On the previous lesson we solved the question A, and so the question B states, on which of the two machines, the machine A or the machine B, was the capture made? Identify 3 mechanisms, 3 different mechanisms to find this out, and also which one or which ones of these mechanisms can be used in this problem, and also justify why. So as we analyze this trace and we analyze this capture, we can see that the capture was made in the machine A. And now we are going to explain and we are going to justify why, okay, we know this. First of all, in a general way, okay, we can use the following 3 different mechanisms, as the problem statement specifies, to identify which machine we are making the capture. And we are here seeing the trace. The first mechanism is by analyzing the times of each sequence number, and basically the time that it takes for each of the segments to arrive. So essentially, based on the times between 2 consecutive segments, we can know where we are. Essentially, very small times imply that we are on the side of the sender of the second, and if the time is greater, such like on the order of a round-time trip, then it will be the opposite. We are going to see that this is an option, and it is a viable and feasible mechanism that we can apply on this problem. We are going to see in a moment how. The second mechanism is by analyzing the losses or the repetitions. Essentially, if repetitions take place and are seen in the capture, so essentially we send segments more than one time, so if there are repetitions, this means that we have been having losses and we are therefore on the side of the repeater. Finally, we can also analyze the private addresses. If we see a private address, then we are on that machine. So for this problem and for this trace, for this problem 1, we can only use 2 mechanisms. And these are the first 2, the times and the losses or repetitions. Let's begin with the times. These times are seen very clearly in the connection establishment. And for instance, if we analyze this connection establishment in here, the first column that we see, what is? It's the column of the time. So let's analyze the time. So between the first synchronization and that we send from the client to the server, remember, from the application A to the application B, we also saw in the previous question that the one that initiates the connection is the application A. So of course we begin with time 0, and then we receive the response, which is the synchronization plus the acknowledge from the B server. As we can see in this packet from the application B, we see that we have a time 0.1, okay, 00374. We can see the times in seconds, so the difference between this one, 0.100374 minus 000, is essentially 0.100374. So this is the difference between the synchronization and the first response from the server in this three-way handshaking in the TCP connection establishment. With the first segment we send at time 0, and the second we send at this time 0.1 and the value, which is this value in here. Okay, this essentially means that here we have this time, and this time is precisely the value of a round time trip. And so the reason that this is the round time trip is, as we can see, if we analyze now the third packet, the time frame, this gives us 0.100483. This essentially means that this time that we have between the synchronization and the acknowledge, and this acknowledgement is this value minus this value. There's a difference. So this difference in here, this value minus this value, gives us this time in here in seconds. As we can see, this first time, okay, is much higher and considerably higher than this one. Okay, this means thus that this is the round time trip, and moreover, we are making the capture in the machine A, which is the machine that initiates the TCP connection establishment. Since here in the times it is seen very clearly that in the connection establishment, between the synchronization and the synchronization acknowledgement from the server, there is a round trip time, while between the synchronization acknowledgement from the server and the acknowledgement from the client, there is a much lower time. And so if the capture, and this is why this is very important, if the capture was made in B instead of in the application A, if the capture was made in B, then the bigger time, okay, will be between this synchronization and acknowledgement and this acknowledgement. If we see that the last two segments have a bigger time than the first two ones, this means that we are making the capture in B, but this is not the case here. The case that we have here is that the time between the first segment and the second, between this one and this one, is much bigger than between the second and the third. Therefore, we conclude that we are making the capture in the application A. Okay, so this fundamental of once we know where do we start, because remember that we always start in the client, okay? Once we know where we start, if we have a very bigger time between the first segment and the second, it means that we are making the capture in the client side. But if we have instead a bigger and much bigger time between the second segment and the third one, it means that we are making the capture on the server, okay, on the receiver. So this is very important. It's very important to understand this. There you go. So now let's justify how the second mechanism can also be applied in this case, in this situation. Remember that if repetitions are seen, it means that we are on the side of the sender, of the repeater, the one that sends over and over again. So as we can see in this trace, we can see data segments that are sent more than once. Okay, this means that we are on the sender side. Essentially, we can conclude from this that we are on the application A. Where are those segments that are being repeated? Well, for instance, just consider this segment which has the line 4 that has this sequence number. Clear, right? We consider this segment. What happens? It has this sequence number, but just after, we wait a while at the time 8, okay, and here, not the time 8, but the segment 8 that we send, we also send this same data segment. So the 8th segment, the segment number 8 that we send, is the same segment as we send in the 4th segment. It is this same one. How do we know it is the same one? Well, because they have the same sequence number. Okay, as we can see, the sequence number is the same. And with this is enough. In fact, this is repeated one more time, as we can see. The data segment, the TCP segment that we send on the position 11, okay, we also send again, once again, the same segment. But here, one repetition is enough to conclude that we are on the sender side. So we are on the application A. We are on the machine A, that is, it is the machine A, okay, this machine A that is performing this trace, this TCP dump and this TCP capture. Whenever we see repetitions, okay, it is because we are on the sender side. Finally, the third mechanism, as we discussed before, cannot be applied in this case, since we have no private addresses to be appeared in this TCP dump. Okay, as we can see in this trace, there are no private addresses. All of the addresses that we see there are public addresses, so we cannot apply these third mechanisms. But we can apply the first two. Okay, and with both mechanisms, of course, we arrive to the same conclusion, that the capture was made in the machine A. Very well, with this, we end the solution to this question B of the problem 1. We remind the student that you can download both the solution to this problem as well as the statement on the downloadable documents of this lecture. Hey everyone, on this lesson we are going to continue to solve now the question C of this problem 1. So in the question C of this problem we have taking into account the information available, what is the round time trip approximately? Remember that this RTT stands for the round time trip, or the round trip time. Okay, the round trip time is the duration measured commonly in milliseconds from where a browser sends a request to when it receives a response from a server. It is one of the main factors when measuring the page load time and also the network latency. So here we need to give the round trip time. Also, what is the actual effective speed of the connection? We need to give this as well. And finally, we have these two last questions. What maximum effective speed could we achieve if the application A were to send to the application B a very large file? And what has to happen to be able to reach that maximum effective speed? So this is the question C, the point C of this problem 1. So remember, what do we know so far? Well, on the previous questions, A and B, we saw that the one that is doing the capture here is the application A. Right? We also saw that the application A is the only one that is sending information. B doesn't send anything to A. And now here let's begin in this question C to compute here the round trip time. Here to compute the round trip time is very simple. In fact, we already introduced this notion of the round trip time on the previous lecture when we were trying to gather which application is doing the capture, and we saw one mechanism which was doing times and calculating the times between the packets, the times between the frames. And so we introduced that some of these, okay, differences was the round trip time. So let's review this idea. So to begin with, to compute the round trip time here is very simple. The only thing we need to do here is to compute, okay, and see the difference in time of the first packet and the second one. Why? Well, remember, because these first three packets, this is the TCP connection establishment. Remember, in a TCP connection establishment, we first have the synchronization from client to server. This is the synchronization. Then we have the response from the server, okay, with the acknowledgement. That means that we can send information from the server to the, in this case, from the client to the server, okay, we can do that. However, we also need to be able to send information from the server to the client. That's why we also need here to request a synchronization. And finally, the last frame, okay, in this three-way handshaking process is the acknowledgement from the client. And so now we are able to send information from the server to the client, right? This, we already know that. And since, moreover, since we know that the capture is being made on the application A, the round trip time is going to be that very big time, okay, which is the time between this happening in here. Essentially the time between we send the synchronization and we receive here the synchronization acknowledgement. So this difference, essentially, as we can see here, is 0, okay, essentially this value, which is 0.100374 minus 0. If we compute this difference, we can see that the round trip time is this value in here. In fact, keep in mind that it is evident in here that the round trip time is not going to be the difference between this and this. Why? Because this difference is very small. We already said this before. Okay, here the second segment and the third one, the difference between these two is a value that is very, very small. And this is clear because the capture is being made on the application A. Now, if the capture was being made in the application B, in the server, then the big difference time will be between the second segment and the third segment. Between the first one and the second, we will have a very little difference. But this is not the case. We are making the capture in the application A, in the client. That's why the big difference is between the first segment and the second, and so hence the round trip time is this difference. So here we already said that the first solution here, the round trip time is about 100 milliseconds. Keep in mind that since this value is in seconds, okay, we need to multiply by 1000 to get the milliseconds. So this gives us around, okay, 100.374 milliseconds, right? And we here forget about this 0. Okay, so this is the approximate value in milliseconds. If we leave it like this is the value in seconds. Because remember, in this column time of the TCP dump, okay, this is the value time in seconds. And in fact here, and not only in the very beginning, that's essentially this is what we recommend to do to calculate the round trip time very easily and quickly. However, note that we can also calculate this round trip time, the estimation of the round trip time in other segments, in other differences of the segments inside this frame capture. Keep in mind that between the shipments and the packets 11 and 12, we can calculate the round trip time as the difference between those two, and also between the 13 and 15. In fact, if we here analyze the packet 11, it is a packet that comes from the application A to the application B, right, with this, as we can see here, okay, value of the sequence number. And then just after we have the confirmation. This confirmation is about 100 milliseconds, okay. In the same way, the 13, it is a packet from A to B, and then on the 15 we have the acknowledgement, okay, from B to A, and again we have around 800 milliseconds. In fact, it is more precisely to compute the round trip time with this last example, the 13 to 15, because in fact what we can see in here is that on the packet 13 we are sending, okay, a data frame with the sequence number, this one that we see here, 17593, and here on the 15 we have the acknowledgement of this same sequence number. That's why it is very precise. On the 1112 we have the acknowledgement of another sequence number, so it may be not that precise, but on these 13 and 15 we have the sending, this is the packet 13, and on the 15, on this packet 15, we have the acknowledgement of the segment that we have sent before, so with the same sequence number. And in fact, here we can see that this is roughly, okay, almost the same value that we see here in the first case, so which is about 800 milliseconds. Okay, so now let's continue computing the maximum effective speed. Or in this case, first of all, let's compute what is the actual effective speed that takes place, and then we are going to continue to compute the maximum one. Let's begin with what is the actual effective speed that we see in this capture frame on this TCP connection between A and B, between these two applications. So first of all, we need to have, this is going to be a computation of the quotient to calculate the actual effective speed. We are going to have here on the numerator the number of bytes. Okay, so here is the number of bytes, the amount of bytes that we have sent so far. Okay, and here the time in seconds. Okay, this is the time that we have in seconds. Right, so if we do this fraction, okay, from the capture, we are going to have the actual effective speed. So let's compute it. First of all, we need to search for the last frame that we send from the application A to the application B that contains data. Okay, keep in mind that the last one is the packet 18, okay, that we send from the application A, which has this port to the application B. Now, some of you may say, well, what about the packet 20? It's also a packet that you send from the application A to the application B. Yes, this is true. However, this is an acknowledgement. It is a confirmation. Okay, it is confirming here the last packet from the server, which is application B. So this is not interesting for us because this is a acknowledgement. We want to study the last frame, the last TCP segment that we send from the application A to the application B that has data. And this is this one in here that we see. It has this sequence number, okay, which is this one that we see, 2241. We already know that we have this sequence number. However, remember that the amount of octets that the application A sends to B, we already calculated this on the lecture to the question A, and it is this one, okay, because the last one of the finalization, this doesn't count, so we need to subtract 1. So this gives us 20,240. This is the amount of bytes that the application A sends to B. Very well, we already have now the numerator. So since here we have the bytes, this is 20,240. This is the amount of bytes. And now what about the time? Well, we can see that this time in total, we only need to look at the last one, and this is around 4.15. okay, if we here round this value, for here we need to count all of the segments. So the last one that we see here until the TCP connection finishes, it is this one. So it is 4.15. So here the time is 4.15 seconds. However, we need to subtract here from this time the time of start of sending the data, okay, just after the acknowledgement of the TCP connection establishment. And this is precisely at this time in here, okay, which is around 0.1 seconds, as we can see. Okay, we need to subtract 0.1, okay. And now, commonly what we have, when we have to compute and to give the effective speed in a TCP connection, we commonly do this, and we represent the solution in the unit bits per second. Bits per second. Of course, what we have in the numerator is in bytes, so we need to transform these bytes to bits, and it is very simple. Remember that 1 byte, 1 octet is equal to 8 bits, so here we only need to multiply this by 8, right? With this we have the value in bits. So here we have bits, and here we have seconds. So when we make this division, we'll have bits per second, right? So let's compute this. And this gives us a value of around 39,980 0.24 bits per second, that we can round this as well, okay, and this is around 40,000 bits per second. Okay, this is the approximate actual effective speed for this TCP connection, right? As we can see, very simple. We write the number of bytes in the numerator, we transform these 2 bits, and below on the denominator we have the time of the TCP connection, and we need to subtract the time to establish the TCP connection. Which time, okay, this is time that we are not sending data at all. Remember, on the TCP connection establishment, we only send the TCP header, we don't send any data. So this is how we compute the effective speed of this TCP connection. Let's now continue with what maximum effective speed could we achieve if A were to send B a very large file, and what has to happen to be able to reach that speed. Here, the maximum effective speed, okay, that we can achieve if A were to send a very large file to the application B is an effective speed where we send a value in bytes of the advertised window, okay, and in one round trip time. Essentially, remember that the advertised window, okay, we can get the value of the advertised window in here, this win. Then just after the win we have here in the TCP DAM, this value, this is the value in bytes of the advertised window, the size of the advertised window in bytes. So that we need to send the steady state window, this is the same as the advertised window, in one round trip time. So we already know the value of the steady window, of the advertised window, which is this one. Okay, we can see here on the frame, on the TCP DAM frame, it is 11,584. Here we have 11,584. This is the advertised window. So we want the effective speed, the maximum effective speed, once again in bits per second instead of bytes per second. So we just transform this value to bits. So we can just multiply by 8, because if this value is in bytes, in unit bytes, we multiply by 8, and so we have now the value in bits, right? And we divide this by the round trip time. Remember that the round trip time is this difference between these two first segments, which is 0.100374. So here we are rounding this, okay, is to 0.1, okay, and this gives us a total amount of 90, or in this case 926,720 bits per second. This is the maximum effective speed that we can achieve, okay, if the application A were to send to the application B a very large file. Once again, we need to send the size of the advertised window in only one round trip time. This means that we have the maximum effective speed, right? And so what has to happen to be able to reach that speed? Well, if we want to, whenever we want to be able to reach the maximum effective speed in a TCP connection, the condition, okay, is that there should be no losses in the TCP connection. Because if we have losses, it will be impossible to send the size of the advertised window in one round trip time, because we are going to resend packets that were already sent before. Right? So the time is going to be bigger, and so the effective speed will be minimized. If we want the maximum effective speed, we also need the condition that there should be no losses in the TCP connection. Very well, so with this we finish the solution to the question C. As we can see, this question C is a very complete question. We review many notions in regarding study and the analysis of a TCP DAM capture. We also know how to compute the round trip time, how to compute the actual effective speed, how we can analyze the maximum possible effective speed that we can achieve, and which condition will allow us to have this maximum effective speed. On future lectures, we are going to continue to solve the question D of this problem 1. On this lecture, we are going to solve the question D of this problem 1. So on this question D, okay, it states draw the evolution in time of the congestion window during the entire sequence from the sequence 1, okay, to here the frame 20. Indicating the phases of the slow start and congestion avoidance algorithm. Remember, we already studied this algorithm. And finally, it also states, and here asks us to justify if there is any anomaly in the evolution of this congestion window and the evolution of this window. So, since this is a question where we need to draw the evolution in time of the congestion window, okay, during the descending of the 20 frames, we will have a plot. Right, we will have a graphical representation. And so what is important here is that we look that the first correct information that we have is at the exchange 6, because on this exchange 6 is where we have the first retransmission. Here it is very simple to see that, for instance, in the sequence of the packet 1, in this packet 1, we are sending the data from the application A, the client, to the application B, the server, that has this sequence number. And then the server confirms, acknowledges this sequence number. On the third packet, we're sending this sequence number from A to B. On this fourth packet, we're sending this, okay, sequence number from A to B. On the packet 5, we have the acknowledgement from the server of the packet that we sent initially, which is the 1, right? But now what happens? On the packet 6, we have precisely, okay, a sending from the application A to the application B, and this sequence number is precisely the same sequence number as the exchange 1, as the first packet 1. This means that we have a retransmission. So whenever we have a retransmission, following the slow start and the congestion avoidance algorithm, remember that what we do is we set the congestion window to be 1 maximum segment size. Whenever we have a retransmission, this is what we already studied on the lecture on the slower start and congestion avoidance algorithm, which is an algorithm that combines two mechanisms. This form part of the flow control, but they have the role for the congestion control. So this algorithm, okay, the slow start and congestion avoidance, is an algorithm in TCP that belongs to the congestion control in TCP, where we use this control, the congestion control, to compute the value of the congestion window. In fact, as we can see, this algorithm uses the idea to compute the value of the congestion window, which is the CWND. We don't use here the advertised window. It is an algorithm to compute the value. It is a dynamic value because this value is going to be updated as the sequence gets more and more sequence, so as the time goes by, this value of the congestion window is going to be modified. Now remember that we have two phases. We have the phase of the slow start, where we keep incrementing the congestion window in one maximum segment size, and then we have the congestion avoidance, where we increment this congestion window to a given proportion, right? So the most important part here to remember from this algorithm, where we are going to begin with by explaining this question D, is to remember that whenever we have a retransmission, we are going to set the congestion window to be equal to one maximum segment size. So here, very simply, we can already begin to draw, because at the exchange 6, as we can see here, we have a plot, a very simple plot, where the x-axis is the time t, the time of the sequence. Remember that we have time 1 to time 20. This is the number of the packet. In this sequence from 1 to 20, we have the packet 1, packet 2, and so on. So this time t is the time of the packet that we send, You can also see here the order of the packets. So, and then we have on the y-axis, very important, what we have. We have the congestion window, but we divide the congestion window by the maximum segment size. So that in these ways, as we do this division, we can work with natural values. Remember that the congestion window has a value in bytes. It is a value in bytes. So of course we are going to have here, we can even have very big values for the congestion window, but we don't want to work with very big values in this plot. We want to have a very easy visual representation. So we can divide this by the maximum segment size, because remember that at the exchange 6, since we have a retransmission, we set the congestion window to be equal to the maximum segment size, right? The congestion window is equal to one maximum segment size. So as we divide the congestion window by the maximum segment size, this gives us equal to 1. So very simply, we can see here that at the exchange 6, we can know for sure, we can guarantee that the congestion window has the value 1 maximum segment size. Keep in mind that all of this graphical representation, the value in the y represents the number of maximum segment sizes. This is 2 maximum segment size, 3 maximum segment size, and so on. So before the exchange 6, we can't know for sure the value of the congestion window. It is impossible to know it. However, from the exchange 6 and from now on, we can know this value. So remember the algorithm. We begin here and we set the congestion window to be equal to 1, and then when we receive the acknowledgement on the exchange 7, keep in mind here what we have. On the exchange 7, we have the acknowledgement, and this acknowledgement this is an acknowledgement of a new data. We hadn't received before the acknowledgement of this sequence number, right? 13,921. No, this is the first acknowledgement of this data. So it is new data. And remember, whenever we have an acknowledgement of new data, following the slow start and congestion avoidance algorithm, we are going to increment the congestion window in one maximum segment size unit. So every time a new acknowledgement arrives, a new one, not repeated, we are going to increment the value of the congestion window in one maximum size, always when the congestion window that we have at the moment is less than the slow start threshold. Now, this slow start threshold, we are going to talk about that, but keep in mind that since when we have the exchange 6 and we have a retransmission, the congestion window drops to one maximum segment size, of course the threshold is going to be bigger than one maximum segment size. We are going to discuss what is the threshold, but we can already see that we are in the phase of a slow start. The congestion window, which is at the moment 1, is less than the threshold, so we increment the congestion window in 1. So that on this exchange 7, we are going to have 1 plus 1, so we are going to have 2 maximum segment size. That is why here on this exchange 7, we increment, right, the value of the congestion window in 1, because we have this acknowledge of new data. Here we have also the explanation. Keep in mind that when we receive this acknowledgement, it is new data, so the congestion window goes up to 2, we increment it in 1, so now the value is 2. And now the window does not go up again, as we can see here. And the reason for this, okay, is because there are no more new acknowledgements of new data, until there is a retransmission at the exchange 11. Keep in mind, if we study this TCP dump capture from the exchange 7, we don't have more new acknowledgements. In fact, here we have a sequence number that we are sending, here we are also sending, here we are receiving, but this acknowledgement of this sequence number was already seen before, in fact, right? So this acknowledgement of the exchange 10 is not a new data acknowledgement, so we are not going to increase the congestion window in 1. And then what happens? Well, just in the exchange 11, we have, just in here precisely, we have a retransmission. Here we have a retransmission. This retransmission is for this sequence number. Remember that we already sent this before, right? We sent this sequence number in here. So we are having a retransmission. Since we're having retransmission, we are going to now decrease the value of the congestion window to 1 maximum segment size. Remember, whenever we have a retransmission, the congestion window value drops to 1 maximum segment size. So once again, when we have the exchange 11 from the value 2 that it had before, it drops to the value 11. Keep in mind that between these segments, between the segment 7 and the segment 11, since we don't receive new acknowledgement data and we have no retransmissions, the congestion window remains constant. As we can see, it remains constant, right? On the exchange 11, it drops to 1 maximum segment size. And then what we have? We have just at the exchange 12, on the segment 12, we have an acknowledgement of this sequence number, 16,845. And this is precisely a new acknowledgement. It is an acknowledgement of new data because we haven't seen any acknowledgement before of this data in here, of this sequence number. So, since this is a acknowledgement of new data, we know for sure that the value of the congestion window, since it is 1 at the moment, is less than the threshold, we are going to increase the value of the congestion window in 1 unit maximum segment size. So instead of 1 maximum segment size, we have 2, right? So on the 11, we here see on the exchange 11, it goes to 2, okay? We increase it to 2 once again. So now we need to here compute what is the value of the slower start threshold. This is an important metric. We need to know the value of this threshold to here plot correctly the data and the plot, okay? Of course, what we know is that whenever we have a retransmission, in this algorithm, when we update the value of the threshold as the maximum between 2 maximum segment sizes and window divided by 2. Now here, this window, okay, the congestion window, we assume that this is a bigger window than the advertised window. So here we can also assume that this is the congestion window. And so remember, when we had a retransmission, the value of the window, we know the value of the window goes to 1 maximum segment size. So 1, okay. And then we increase it in 1. And so now, as we have a loss, we here need to compute the maximum between 2 maximum segment size and the window, which is 2 divided by 1. In this case, divided by 2, this gives us 1, right? So whenever we have this loss, the maximum between 2, okay, maximum segment size, keep in mind that what we are computing now, essentially, is on the exchange 11, since we have this retransmission and the value of the window is 2, the value of the window is 2, okay? And now we need to compute the value, okay, between 2 maximum segment size and the value of the window, which is 2 divided by 2, which gives us 1, right? So we are right here computing the threshold, the maximum between 2 maximum segment size and the value of the window, which is 2 divided by 2. This gives us 1. So the maximum between 2 and 1, what is? It is 2. So the maximum is 2, and so the threshold is equal to 2 maximum segment size. So with this, we conclude that this is the value of the slower start threshold, okay, 2 maximum segment size. And so now at this point, when we are on the exchange 12, okay, we here have no new acknowledgements from this range. We have on the 13, we don't have a new acknowledgement. 14, we don't have a new acknowledgement. But look at here. on the exchange 15, we do have a new acknowledgement of this sequence number, right? 17,593. So since we have a new acknowledgement, we need to compute the body of the algorithm. And so this is every time a new acknowledgement arrives. So we have two cases. If we have that the congestion window is less than the slowest start, we increment in 1. If the congestion window is equal or greater to the slow start threshold, it means that we are on the congestion avoidance phase. And now we need to increase here the congestion window plus 1 maximum segment size multiplied by the maximum segment size divided by the congestion window. So where are we at this point? Well, on the exchange 15, just as the exchange 15 in this one where the new acknowledgement arrives, we are precisely in the case where the congestion window is equal to the slow start threshold. As we can see, it is equal. So since this is equal, we are now on the congestion avoidance phase. So we are not going to increase the value of the congestion window in 1. Instead, what we are going to do, we are going to increase the value of the congestion window in the maximum segment size, so 1 maximum segment size, multiplied by 1 maximum segment size divided by the congestion window. We can here substitute, and this gives us the actual value of the congestion window, which is 2 plus 1 maximum segment size, multiplied by 1 maximum segment size divided by the congestion window, the actual one, the current one, which is 2. So this gives us 2 plus 1 multiplied by 0.5. 2 plus 0.5 is 2.5. So at this point, okay, on the exchange 15, we increase the congestion window from 2 to 2.5, as we can see in here. Right, so very important to remember the algorithm and follow the ACE algorithm of the slow start and congestion avoidance. This is key to solve this question D, since it is a question about this algorithm of congestion control and about how this dynamic congestion window evolves during the time, right, and changes over time. Also, we increase at the exchange 15 from 2 to 2.5, then we have the exchange 16. We don't have new data acknowledgement, neither we have retransmission. This is the first time we transmit this sequence number. And then at the exchange 17, we have an acknowledgement of new data. And since we are on the congestion avoidance phase, and at the moment on the 16, we have the congestion window to be 2.5. Okay, now we need to do the same formula, we need to apply the same formula. However, now the actual value of the congestion window is 2.5. So since we have 2.5, this gives us 2.5 plus 1 multiplied by 1 divided by 2.5. This gives us a 2.9, which is roughly a value of the congestion window to be 3. Right, so this basically gives up to 3. Okay, approximately. This is really 2.9, but here we use to use natural numbers and not to work with float numbers. We use here 3. You know what happens? If we analyze now the segment 18, the exchange 18, what we have? Oh, we have precisely a retransmission. So since we have a retransmission, what happens? Well, following the algorithm of the slow start and congestion avoidance, if there is a retransmission, then the congestion window is equal to 1 maximum segment size. So at the exchange 18, at the segment 18, the value of the congestion window drops down to 1 maximum segment size. And now, finally, on the segment 19, on the exchange 19, we have an acknowledgement of new data. This acknowledgement has never been seen before. Okay? And so, since this is an acknowledgement of new data, we here need to increase the value of the congestion window, and since now the value of the congestion window is 1, of course the congestion window is less than the threshold, so we are not going to apply the formula of the congestion avoidance. Instead, we will use a slow start, because now we are in the slow start phase. We are not in the congestion avoidance phase, so we increase the value of the congestion window in 1 unit. So 1 plus 1 gives us 2. So at the exchange 19, the value of the congestion window goes up to 2. Very well. So with this, we draw the evolution in time of the congestion window. Here we also have the explanation step by step of the slow start and congestion avoidance algorithm to follow this plot. Finally, on the question, is there any anomaly in the evolution of the window? Well, there's no anomaly in here, because as we can see, we have first a phase of a slow start, then we have a phase of the congestion avoidance, and finally another phase of the slow start. And so there is no, as we can see here, there is no anomaly in the evolution of this window. Very well, so with this we finish the solution to this question D. We remind the student that you can download both the statement of this problem as well as the solution on the downloadable documents of this lesson. Hey everyone, on this lecture we are going to solve the question A of this problem 1, which is the last question of this problem. So in the previous question we saw and we draw the evolution of the congestion window, okay, during the sequence from the packet 1 to the packet 20 in this TCP connection. And so now in the question E we need to consider this: if after sending the packet 13 there are still 30,408 bytes to send and there are no more losses. Remember, when we say that there are no losses, it means that there will be, okay, hence no retransmissions. There will be no retransmissions. We need to draw the new evolution of the real window until the start of the disconnection. So now we need to draw the evolution of the window, and after sending the packet 13 we will need to draw the evolution. Okay, now again we need to use the slow start and congestion avoidance that we already studied, and we have been working with this approach on the previous question, on the question D. Remember that on the question D we draw the evolution in time of the congestion window during the packets. And so now we need to again come to this plot, and now what we need to consider is that after sending the packet 13, which is this one that we see here, there are still 30,408 bytes to send, okay? And also there are no losses, there will be no losses, so there will be no retransmissions. Remember, whenever there is a loss, whenever there is a retransmission, okay, the retransmission timeout pops, it jumps, and so we set the congestion window to be equal to 1 maximum segment size. This will not happen because there will be no retransmissions as this statement specifies. So first of all, let's reason with this information about the number of bytes we have left to send. So if we have 30,408 bytes, and we know from the TCP dump capture that the maximum segment size is this one, as we can see, the maximum segment size is 1,448. This is the value of the maximum segment size, as we can see here in this capture, right? Whenever we have a TCP establishment, as it is here the first 3 packets of the 3-way handshaking process, this MSS specifies the maximum segment size. So if this is the number of bytes that we are left to send, and we know that one maximum segment size, one MSS, has the value of 1,448 bytes, then this is going to give us the number of segments that we are left to send, right? So if we make this division, this gives us a value of 21. So 21 maximum segment sizes are going to be the total number of maximum segment size segments that we are going to send. So now remember, before the package that we sent, we had that the congestion window was equal to 2, okay? And so now at remember that on the time 12 we incremented in the slow start phase the congestion window to 2. So if before the package 13 we had the congestion window of 2 and we had just entered the congestion avoidance phase, remember that the congestion avoidance is a phase where the congestion window is equal or greater than the slow start threshold. Remember that the slow start threshold we here discussed on the previous lecture, it was 2. And so after the 13th package there will be a new shipment, and upon receiving the 2 acknowledgements we will have a congestion window equal to 3, and from there each round trip time the congestion window will increase by 1, okay, when the acknowledgements of the previous window are received, that is 3, 4, 5, 6, okay. So after sending 13, we will eventually have sent 1 plus 3 plus 4 plus 5 plus 6, okay, which gives us 19 maximum segment sizes. And so we will have 2 left until we are 21, which will lead to a final window, as we can see here, using the congestion avoidance phase, the actual window, which is 7, plus 2 divided by 7, okay, which will give us in this graph, as we can see, this congestion window value, which is roughly 7.28. What is important is here to mention that the advertised window, as we know in the TCP frame, in this TCP DAM capture, the advertised window is this value, 11,584. We already explained on the previous question, on the question D, that this win that we see here on the capture represents the advertised window. This is the advertised window. The advertised window has this value in bytes. If we want to know how many maximum segment size it occupies, okay, the window, we can just divide this by the value of a maximum segment size. So the advertised window is 8 maximum segment size. However, okay, along as we send all of the 21 maximum segment size in this TCP connection, the congestion window would have reached 7.28 only maximum segment size. So we will not have reached the advertised window. In other words, the congestion window will never reach the advertised window. That's why in this plot, we can see here, okay, we can draw now the new evolution of the real window until the start of the disconnection. Keep in mind that here we are considering the case from the package 13. Okay, essentially we continue this graph that we saw before, but now instead of beginning from time 1, we begin from the time 13, from the exchange 13. This one that we see is the third. In fact, this 0, this origin of the plot is the exchange 13, and now we have that the x-axis is 1 round trip time. So at each round trip time, the congestion window will be increased by 1. This is what happens in the congestion avoidance. And then the final increment, as we see, this is 7 plus 2 divided by 7, so we will never reach the value 8, which is the value of the advertised window. Very well, so with this we finish the solution to the question M. It is a question that is very linked with the question D, right, to draw here the evolution of the congestion window in this TCP connection. And so with this we finish the solution to this problem 1. We remind the student that you can download all of the solutions and the questions of this problem on the downloadable documents of this lecture. Hey everyone! On this lecture, we are going to introduce and present the problem 2 on the collection and solve problems on transport protocols. On this lecture, we are going to solve the question A of this problem, and also we are going to introduce this problem. So this problem 2 states, in the network in the figure that we see here on the left, there are 20 computers, 20 PCs, 10 connected to the router R1 and 10 connected to the router R3. That send data to the server, each with a TCP connection that at maximum speed, okay, that allows. So we also here send the data, okay, at the maximum speed that is allowed in this network. Assume the following answer, okay, and assume to following this notion. So here we need to assume a given sequence of notions and assumptions to answer the following questions that are going to be in the next slide. So the first assumption, all links are 10 megabits per second. So this is basically indicating for us the speed, okay, of the links. Assumption 2, routers have a memory of 2 megabytes, right, that can store all datagrams waiting to be transmitted, and datagrams that arrive are discarded if the memory runs out. Very well. Assumption 3, all TCP sockets on the PCs and the server have a receive buffer of 60 kilobytes. Assumption 4. Assume, for simplicity, that the size of TCP and IP headers is 0, and the maximum segment size is 1500 bytes. Assumption 5. The link delays is 0. Assumption 6. The acknowledgements transmitted by the server are never lost and reach the PCs immediately. TCP always sends acknowledge when receiving data, only implements the slow start and congestion avoidance algorithm. Remember, we already studied this algorithm, and it is as efficient as possible. Okay, this means that the acknowledgements are going to be sent immediately and the process time is 0. And finally, the assumption 7, the last assumption, the connections are persistent, meaning that the connections have been established for a long time. And so, given all of these assumptions, once again, all of this information is what we need to assume to answer the following questions that we are going to see now. We also need to justify our answers. So in this problem 2, we have a collection of questions from the question A until the question G, together with H and I. So we have all of this series of questions. And so in this lecture, we are only going to solve the question A, okay? And the question A states, say what is the effective speed, that is the throughput, that each TCP connection will achieve. So this effective velocity, this VF, is what we need to calculate, okay? The velocity is the same as the speed that each TCP connection will achieve. So this question is very simple. Keep in mind that since all of the PCs, okay, are transmitting data to this server, so the 10 PCs, okay, over R1 we are transmitting information to the server, also the 10 PCs are basically transmitting information here to the server. What is going to happen? Remember that here the first assumption, all links are 10 megabits per second. This is the maximum speed that we can transmit over a link. So essentially what we have is the configuration like this. All of the links that we have here between all of the interfaces are 10 megabits per second. Essentially from here we can send 10 megabits per second, also here 10, okay, and also here 10. Keep in mind that all of the PCs that we have connected here on the left and on the router 1 and R3, they are sending information, okay, to the server. They are sending data to this server in here. So we have here data that is being sent, okay? However, what happens is that here we have a bottleneck. What is a bottleneck? So in networking, a bottleneck refers to a point or component within a network where the flow of data is significantly restricted or limited. This happens when the capacity of or performance of a particular network element becomes a limiting factor for the overall network speed or efficiency. So in this case, why R2 is a bottleneck? Well, because here if we are sending information, data at 10 megabits per second, and here also 10 megabits per second, remember all of the data links, also this one and this one, they have 10 megabits. So here we also have a maximum speed of what? Of 10 megabits. However, here we are arriving 20, okay, in total, because 10 from here, we have arriving 20 megabits per second. However, if we try to send 20 megabits per second in here, this will not be possible because all the links have a maximum speed of 10 megabits per second, okay, as we can see on the first assumption. That's why this is a bottleneck. So what is going to happen here? Well, we are going to transmit, essentially, 10 megabits per second, and we are going to take here 5 from the router 1, and also we are going to take here 5 from the router 3. Keep in mind that here they are distributed equally, since no other priority assumption has been specified in the statement, so we treat all of the interfaces equally with an equal distribution, and so therefore, what is going to be the effective velocity of the effective speed? Well, if we're sending 10 megabits per second and we have 20 PCs, then the effective velocity, this effective velocity in here, is equal to the amount of data that we are sending, in this case 10 megabits per second, divided by the total amount of PCs, okay, that are sending, in this case 20 PCs. So if we make this division, this gives us a effective velocity of 0.5 megabits per second, and this is the solution to this first question A. Right here we can see the justification. The bottleneck will be at the R2, okay, and we are going to distribute it equally between the PCs. Very well, with this we finish this short question, the first question into this problem 2. On the following lecture we are going to continue with the question B. Hey everyone, on this lecture we are going to solve the question B of this problem 2. So we already introduced and presented this problem on the previous lecture. We also solved the question A, and so now we will solve the question B. The question B states, say, what is the advertised window on this network, and will it be needed to use the Windows scale option? Well, here let's go by parts. First of all, let's calculate what is going to be the advertised window. So to calculate the value of the advertised window, we need to look closely at the value of the receive buffer or the reception buffer. So here, all of the TCP sockets on the PCs and the server have a receive buffer of 60 kilobytes. Now, remember that in TCP, when data is sent over a TCP connection, it is divided into smaller units called TCP segments. And it is the TCP buffer with a designated area in the receiver's memory where these segments are stored until they can be processed. So how do we calculate the advertised window? Well, remember that the advertised window, okay, here the objective is we use flow control to adapt the transfer rate of the transmitter of the sender to the reception capacity of the receiver. This generates the advertised window. In other words, to calculate the advertised window, we only need to look at the size of the receive buffer. Okay, so now if we look at the size of the receive buffer, we see here that we have 60 kilobytes. So 60 kilobytes is going to be the value of the advertised window. Now, to the other question, will it be necessary to use the Windows scale option? So first of all, remember that Windows scaling is a mechanism that allows for the expansion of the TCP receive window size beyond its default maximum value. So here to reason if we need to use it or not, we only need to look here. We only need to remember that the default maximum window size is 2 raised to 16 bytes, so 65,536 bytes. This is the maximum default window size. So if our window is greater than this size, we will use Windows scale. Otherwise, there will be no need, since if it is smaller, the default window size provides sufficient granularity for flow control and efficient data transfer. And this is precisely our case. The Windows scale will not be needed because the advertised window is 60 kilobytes, which is a value, okay, less than 2 raised to 16 bytes. In fact, here 60 kilobytes is equal to 60,000 bytes, and so again, this is smaller than 65,536 bytes. So we conclude that we don't need to use Windows scale for this situation. And so with this, we solve this question B, also a very short question and easy to solve on this problem too. We remind the student that you can download the problem statement as well as the solutions on the downloadable documents of this lesson as we go question by question and lecture by lecture. Hey everyone, on this lecture we are going to solve the question C of this problem 2 on transport protocols problems. So the question C of this problem states, reason what will be approximately the occupation of the buffers of the router R1, R2, and R3. Also state approximately how many bytes will be in each buffer. Also, will there be losses? So this is a question that comes with many considerations that we need to take in here. So remember that we already introduced this problem and we saw on the question A and B also that we had this configuration. Now keep in mind, here if we need to justify what is going to be the occupation of the buffers of these routers, remember that on the router R1 we are transmitting in here, okay, a total amount of 5 bits per second, and here also 5 bits per second. But what is the total capacity that we can send? Well, the total capacity, remember that each link, all of the possible links in here, we have a capacity of 10 megabits per second. But here we are only sending 5 megabits per second, right? It is not 5 bits per second, it is 5 megabits, but what is important is to remember that all links are 10 megabits per second. However, we also saw that on the question A, okay, we need here to divide, instead of 10, should be 5, because the router 2, if we want to send data to the server, the router 2 cannot send 20 bits per second, 20 megabits per second, because otherwise we will exceed, okay, the total amount of the speed of the link. So we send 5 from the router 1, 5 megabits per second from the router 3, and so now the router 2 is going to send, as well as it's going to receive, okay, in the sum, 10 megabits per second. And so we are sending 10 megabits per second. This is what we already saw on previous questions. Now, what is going to be then the occupation buffers of all of these three routers? Well, first of all, what about the router 1? Let's consider this router 1, okay, this first router, and the sending of the data on this router. Keep in mind that in the router 1, together with the router 3 that we are going to see, on average, 5 megabits per second come out. This is what happens in the router 1. So, since the router 1 has the capacity to send 10 megabits per second, but we are not sending, we are sending only 5, and we have the capacity to send the double of what we send, what is important is that we have the capacity to send more than what we send, then the buffer of the router 1 is going to be empty. So, the router 1 buffer, okay, is going to be empty. And the reason for this is because we are sending here, okay, in a speed less than the total capacity. Right? The same happens with the router 3. On average, we send 5 megabits per second, which is less than its capacity. So we here have also that the buffer of the router 3 is empty, right? Now, what about the router 2? Remember that R2 is the bottleneck, right? It is the bottleneck, and as it can receive up to 20 megabits per second, but can only send 10 megabits per second. This is what bottleneck is. So its buffer will be filled with the TCP connection window. Essentially, remember, on the assumption 3 of this problem, all the TCP sockets on the PCs and the server, they have a receive buffer of 60 kilobytes. Therefore, we only need to multiply 20 TCP connections that we have, okay, by 60 kilobytes, which is the size of the buffer, right? So here, the router 2, let's put it in here. Now, the router 2 is going to have a occupation buffer of 20 TCP connections that we have multiplied by the size of the receive buffer, so 60 kilobytes. So this gives us a value around 1.2 megabytes. Okay, this is the value or the occupation of the buffer of the router 2. Again, because this happens because R2 is the bottleneck. We can receive in total 20 megabits per second, but we can only send 10. Therefore, we are going to have here in the buffer, its buffer will be filled with the TCP connection windows, right? Essentially 20 multiplied by 60 kilobytes. Now, finally, on the question if there will be losses, of course, there will be no losses. Remember on the assumption 6, the acknowledgements transmitted by the server are never lost and reach the PCs immediately. So therefore, if there is no losses, the flow control is going to be the one that will regulate the throughput. Right, so here we can see the solution to this question. Okay, all of the solution. Again, the R1 and R3 routers, they will have the buffers to be empty. R2 will have the occupation buffer with 20 multiplied by 60 kilobytes, which is 1.2 megabytes, and there will be no losses, and so the flow control is going to regulate the throughput. With this, we solve this question C. Hey everyone. On this lecture, we are going to solve the question D of this problem 2. We are going to continue with this problem. So the question D states, calculate what is going to be approximately the round-trip time that each of the 20 TCP connections that we have in this network configuration will have. Now, keep in mind that since we want to calculate the round-trip time, and we have this configuration in here in the network, we already saw that these were the actual speeds that we are going to go from each link, and this is the final speed. So the round trip time is going to be the time that we will be inside the queue waiting for the datagram for the segment to be sent to the server. Keep in mind that the 20 PCs are going to send data to the server. However, okay, we also saw that the occupation buffer on the server was this one. And so if this is the occupation buffer, okay, that we have inside the router 2, keep in mind that in the router 2 we are going to have a buffer where we are going to have segments that we want to be sent. However, we have here a queue, okay, that some segments will need to be waiting for each to be sent at the end. So we have here an occupation buffer of 1.2 megabytes. So once we have the occupation buffer And once we have the effective speed, okay, what is the effective speed or the effective velocity? Well, it is 10 megabits per second, right? Therefore, what is going to be the round trip time? Well, the round trip time is going to be the time to be inside the queue. So essentially it is going to be the total size of the occupation buffer in the router 2. So this is 1.2 megabytes. Okay, all this divided by the effective speed or the effective velocity, which is 10 megabits per second. Right, so here we have 10 megabits per second. We can simplify this to have all in the same units, and we can basically have the round trip time to be in seconds. So we can rewrite this in here. And so essentially what we can do now is, for instance, here we have megabytes. Okay, we can transform these megabytes to megabits by multiplying by 8, because we know that 1 byte has 8 bits. So this is 1.2 multiplied by 8. And this is the value in megabits. This is megabits now. And here we have on the denominator 10 megabits per second, right? 10 megabits per second. However, instead of having something like this, we can simplify the prefix mega that we know, which is 10 raised to 6 in both numerator and denominator. So we can have something like 1.2 multiplied by 8. Instead of writing megabits, we can write multiply by 10 raised to 6 bits. And the same here on the denominator. Instead of 10 megabits per second, we will have 10 multiplied by 10 raised to 6, which is the prefix mega, bits per second. And as we can see, what we can do now in here, we can simplify this 10 raised to 6 with this 10 raised to 6. And so this gives us 1.2 multiplied by 8, which is 9.6 divided by 10. This gives us 0.96. So what is going to be the round trip time? 0.96. And what is the time unit? Seconds, right? The time unit is in seconds. So this is the value of the round trip time, 0.96 seconds. Now keep in mind that this is the round trip time for each TCP connection. Okay, all of the TCP connections will have this round trip time. Very well, with this we finish this question. Remember that you can download the solution to this question on the downloadable documents of this lecture. On this lecture, we are going to solve the question E of the problem 2. So the question E of this problem 2 states, assume now, and for the following questions, that on average it is wanted to have a round trip time that approximately does not exceed 600 milliseconds. To achieve this, the size of the routers, of the buffers of the routers is reduced. What should be the buffer size that should be set on the router 1, router 2, and router 3 to achieve this? And also, assume that the buffer size is only changed on the routers that are necessary. So, on this question, essentially, what we want to do is, we don't want the round trip time in the round trip time equation, we don't want this value to exceed 600 milliseconds. So, very important, remember that we already saw on the question C what was going to be the occupation of the buffers of the router 1, router 2, and router 3. In fact, we saw that the occupation of the buffer R1 is empty, of the router 3 is empty, and on the router 2, we saw it was 1.2 megabytes. So now in this question, it is evident that we are only going to reduce the size on the router 2, the only one that we can reduce. The router 1 and R3 will not be affected by this statement on the question E. So now in the router 2, okay, the occupation buffer of the router 2 is not going to be 1.2 megabytes. What is going to be? Well, if here we already have the assumption that we don't want to exceed, okay, the 600 milliseconds, then we set here, okay, in this round trip time, the value of 600 milliseconds. So we set here the value of 600 milliseconds. This is going to be equal to the occupation buffer that we're going to have now. Let's just call it this B. All this divided by the effective speed. We already saw that the effective speed was 10 megabits per second. Okay? So we have here the effective speed. So what is going to be now the buffer size? Well, remember that this value is the value in bits, so we have 10 megabits per second. So if I put here the units, 10 megabits per second, and here I want to have the value in bytes, okay. First of all, we need to transform these megabits per second to megabytes per second, and even better, to bytes per second. So to do this, we just pass this. We can transform this to bytes per second, but first let's transform this and pass it in here. So we are going to have to move this value here, multiplying in here because it is dividing, and more formally multiplying both sides by this value. Keep in mind that whenever we say that we pass a value that is dividing to the other side multiplying, essentially what we are doing is we are multiplying by 10 in both sides, okay, and we simplifying here. So what we do formally is multiply in this equation, okay, multiply this equation on both sides by 10. So what we have at the end, okay, this is going to be 10 megabits per second multiplied to 600 milliseconds. So what we can do here is we can transform, and this is going to be equal to the value b, okay. What we can do is transform this 600 milliseconds to seconds. What we need to do is to divide by 1000. This gives us the value in seconds. So this, if we divide, we are going to have essentially 0.6, right? This is 0.6 seconds. This is equal to b. And now we can transform this megabits per second to bytes per second. So first of all, we multiply 10. We multiply this by 10 raised to 6. So now we have, instead of bits, megabits per second, now we have bits per second. And if we want bytes, we divide this by 8. So now the unit of this expression is bytes per second. And here we have multiplied 0.6 seconds. And so this second with this second gets simplified. And so we got bytes. So this is the value in bytes. And if we compute this, this gives us a value of 750, okay, 1000 bytes, which can be simplified as 750 multiplied by 10 raised to 3, which is the same as 750 kilobytes. Okay, remember the prefix kilo represents multiplying by 10 raised to 3. So this is the final value, okay, of the buffer of the R2 that we will need. So 750 kilobytes, which is considerably less and smaller than 1.2 that we had initially, right? Remember that we had initially 1.2 megabytes. Very well, here we can see the full solution. Remember the R2, the R1 and the R3 routers do not affect this this notion because they have empty occupation buffer. So we can leave the 2 megabytes. And then in the router 2, okay, what we want is we want the waiting time in the queue not to exceed 600 milliseconds. So essentially what we do, we have the occupation buffer divided by the effective velocity of the effective speed. This is equal to the retransmission, okay, timeout that we don't want to exceed. We transform this to seconds, okay, so we get 0.6. We multiply this also by 10 raised to 6, which gives us the value in bytes per second because we divide by 8. And so this final, okay, result is the value that we want of b, okay. Now the value of the buffer size that should be set on the router 2. This is the value of the buffer size that should be set, 750 kilobytes. With this we solve the equation E. On the following lecture we are going to solve the question F of this problem 2. In this lecture we will solve the question F of the problem 2. This question F says, say and argue if the buffers from the previous question, the question E, will produce losses, and also what will now be the effective speed, that is the throughput that each TCP connection will have. Among all of the 20 TCP connections, what is going to be also the effective speed. Now, remember what we did on the previous question. On the previous question, we calculated the occupation buffer, okay, of the router R2, because the router R1 and R3 were not affected by this question, so we only needed to modify the size of the buffer of the router R2, and we arrived to the conclusion that the buffer size of the router 2 was this size in here, right? 750 kilobytes. This is what we did on the previous question, the question E. Now, from this, we can now argue if there will be losses or if there will be no losses. Why? Well, keep in mind, on the question C, we calculated the occupation buffer, okay, of the router 2, and we saw that all of the TCP connections, the 20 TCP connections in total, made us a total size of the buffer to 1.2 megabytes, right? This is the total size of the windows that all of the 20 TCP connections will send to the router 2. However, on the previous question, on the question E, we do not have the buffer 1.2 megabytes. What we have instead is 750 kilobytes. Therefore, since this value is far less than the total size that we will need, okay, essentially, of course, there will be losses because this value, okay, is not a node and so far is less than what we need. So there will be losses for the case of this question E that we saw. There will be losses. Once again, because the windows of all of the 20 TCP connections, they have 1.2 megabytes, right? So this so far exceeded the size of the router's queue that we saw. It is 750 kilobytes. So the first question, of course, there will be losses. In this case, there will be losses. Now, what about the effective speed in this case? Well, here the effective speed, it remains the same. Here the effective speed remains the same. Because the 10 here megabits per second continues to be transmitting, okay, in this router 2, and so since we have 20 connections in total, 20 PCs, 20 TCP connections, we only need to divide this speed, okay, divided by 20, and this gives us 0.5, okay, megabits per second. This is the effective speed, the throughput on this TCP connection. So that each TCP connection will have a effective speed of 0.5 megabits per second, because keep in mind, if we multiply 20 PCs that are transmitting at the same time, and we multiply this 20 by 0.5, we get precisely 10, which is the value that we see here in the velocity. So the effective speed remains the same. What is important in this question F, again related with the question E, is that there will be losses because we can't here support all of the size of the windows, which is 1.2 megabytes that we have on the 20 TCP connections, with only the size of the buffer R2 to be 750 kilobytes. Very also, with this we have the solution to the question F. On this lecture we are going to continue with the problem 2. We're going to see now how we can solve the question G. And so the question G, okay, this is the continuation of the question F, and it states calculate now what will be on average the window that each TCP connection will use. This is, we can denote the value of the window as W, and also assume that on average in each essentially in each round trip time, each TCP connection sends a number of bytes equal to the average window, which is this average window W. So to solve this question G, we need to already have solved before and previously the question E, okay, and also the question F. So remember that on the question E we had an assumption that we needed to do, and we needed to follow in the next questions. And so in this question E we calculated the buffer size of the router 2. We saw that the value of this buffer size was 750 kilobytes. And so now once we have this value, the value of the buffer, which is the value that we calculated on the question E, what is going to be now on average the window that each TCP connection will use? Well, the average window, and in fact we can calculate this in two different ways. First of all, we can calculate now the window that each TCP connection will have, as the R2's buffer will be average across the connections. So we can calculate the window W, okay, as the size of the buffer of the R2, so 750 kilobytes, okay, divided by the number of TCP connections that we have, which is 20. If we make this division, this gives us the value of 37.5 kilobytes. Okay, this is one way to approach this problem, and we already see it is very simple. But another way that we can reason about this, we can reason this in the following way. The effective speed will be the average window divided by the round trip time. So therefore, We can now calculate the window W in the following way. This is going to be the multiplication of the effective speed, okay? This multiplied by the round trip time. We already know the value of the effective speed, 0.5 megabits per second. So we can multiply this by 10 raised to 6. This is the prefix mega. So now we have bits per second. And also if we divide this by 8, we have bytes per second. Now we have this value in bytes per second. Okay, and then we put here the round trip time. All of this we multiply by the round trip time. We already saw that the round trip time was 600 milliseconds, which is the same as 0.6 seconds. This is what we saw on the question E. Okay, here we don't want to exceed the round trip time to be a 600 milliseconds, so 0.6 milliseconds. In this case, 0.6 seconds, right? If we transform the 600 milliseconds to seconds, this gives us 0.6 seconds. So we multiply this by the round trip time, which is 0.6 seconds, right? And now as we make this multiplication, what does this give us? Well, if we multiply the numerator and we multiply all this gives us 300,000. And as we divide this by 8, this gives us the value again in bytes, because here we have seconds, here we have bytes per second. So this gets simplified with this unit, and so we have the result in bytes. So the value in bytes is 37,500 bytes. So if we transform this to kilobytes, what we have? Well, we have precisely what we calculated initially, right? 37, okay, comma 5 or 37.5 kilobytes. This is the value of the window, okay? This is the value that will be on average the window that each TCP connection will use in this new assumption that we made on the question E, okay? And we are going to follow for the following question. So here we can see the solution on the question G. Once again, the buffer R2 is going to be average across all of the connections, so we can basically divide 750 kilobytes to divide it by 20. This gives us the value of the window, and also we can reason in this other way. So it is very interesting because both ways, both paths, give us the same result. Okay, so it is another way to confirm and to prove that this solution is correct. So with this, we finish the solution to the question G of this problem 2. Hey everyone, on this lecture we are going to solve the question H of this problem 2. So the question H of this problem states, sketch the evolution of the TCP congestion window that corresponds to the conditions in the previous questions. Assume that the evolution of the congestion window is periodic and draw a period. So we only need to sketch the period of the congestion window, how this congestion window goes evolving as through this period passes. Indicate in the drawing when it will be in the slow start phase and when it will be on the congestion avoidance phase. Remember that here in this problem, we use the congestion avoidance and slow start algorithm. Also, calculate what the slow start threshold is going to be and the maximum value that the congestion window is going to have, is going to get. So essentially, this is the congestion window max value we'll have in each period. Calculate the slow start threshold and the congestion window maximum so that the effective speed and average window are those that we calculated in the previous questions. For this calculation, assume that the time in the slow start is much smaller than the time in the congestion avoidance phase. So let's draw and let's sketch this period. For this, we need to remember the slow start and congestion avoidance algorithm. Remember that at the very beginning, we have the congestion window is 1 maximum segment size and the slow start threshold is infinity. However, we keep changing these values every time a new acknowledgement arrives, right? And in the slow start phase, we keep incrementing the congestion window in 1 maximum segment size, and in the congestion avoidance phase, then we increment the congestion window in 1 maximum segment size multiplied by 1 maximum segment size divided by the value of the actual congestion window. Also, if there is a loss, we here the loss data is retransmitted, and we set once again the congestion window equal to 1, and the slow start threshold to be the maximum between 2, okay, maximum segment sizes, and the window, the actual window, divided by 2. Very well. So for this question, it's very important to remember what we did at the very beginning at the problem, and when we introduced the problem, remember the assumption 6. The acknowledgements transmitted by the server are never lost and reach the PCs immediately. Also, the CPU always sends the acknowledgement when receiving the data, and it only implements this algorithm of a slow start and congestion avoidance, and it is as efficient as possible, right? Very well. So with these assumptions, we can sketch already the evolution of the congestion window as we here evolve the round time trip. In fact, what we have here is the time in round time trip times. This is the round trip times. And so each unit that we see here on the x-axis is one round trip time. And each unit that we see here on the y-axis is one maximum segment size of the value of the congestion window. So of course, at the very beginning, we will have this low start threshold to be a given value, okay, as we evolve, and then we are going to be, of course, in this lower start phase, because this value of the congestion window is going to be less than this lower start. As we can see, this is the value of this lower start. Once we reach this lower start threshold, then we now go to the phase of congestion avoidance. And now, as we can see, this congestion window is incremented with a given factor, right? So as we can see, we keep incrementing in the congestion avoidance phase. Now, what we can see here and how we can calculate now the slow start threshold and the maximum congestion window. Well, as we can see from this plot, okay, we can see that the slow start threshold, as we can see, is the half of the window, of the maximum window. As we can see, just this slow start threshold is going to be just in the middle of the value of the maximum window. So if we divide the maximum window by 2, we have the value of this low start threshold, right? In the other hand, we also have from this plot that the window is equal, as we can see, this window in here that we see, this is the value of the window with this line in here, okay? This line semi-painted and we have very lots of dots. So this value of the window is equal to this low start threshold plus the window maximum divided by 2. And why so? Well, in fact, remember in analysis and in calculus, or in mathematics, if I have a function, if I have a plot, and I want to calculate the value of this point in here, I can just take this as a base, so the slow start threshold is the base, and then we jump to the window maximum, but we want the middle point. So we jump and we divide by 2. With this, we have the value of the window, and so if we substitute that, as we know, this low start threshold is equal to the maximum window divided by 2, and we substitute this in the formula, we get that the window is equal to this low start threshold, which is the maximum window divided by 2, plus what we had before, which is the maximum window, okay, and now, of course, we need to divide this by 4, because we get here the minimum common multiple in the denominator. And now this gives us, if we make this sum, this gives us the maximum window multiplied by the fraction of 3/4. And so, since we know that the window is equal to 37,5 kilobytes, as we already calculated this previously in previous questions, what is going to be the value of the maximum window? Well, we can just substitute. This 3 comes here dividing, and this 4 comes here multiplying. So the maximum window is going to be 4 divided by 3 multiplied by the window, which is 4 divided by 3 multiplied by the value of the window in kilobytes, which is 37,5. We multiply, this gives us 50, of course the unit also in kilobytes. Once we have the value of the maximum window, we can trivially know the value of this low start threshold, because this low start threshold is the maximum window divided by 2. Therefore, we can see that this low start threshold is equal to 50, as we have just calculated, divided by 2, which gives us 25 kilobytes, right? And this is the plot of the period, this is the sketch, and also the value of the maximum window and this low threshold in this question H. So very important to remember that the slow start threshold, okay, is, as we can see, the half of the maximum window. And as we know also, the window, we can express the window as the sum of the slow start threshold plus the maximum window divided by 2, as we can see. And from this, since we already know the value of the window, we can get the value of the maximum window. Once we get the value of the maximum window, we also have the value of this low start threshold, right? Very well, so with this we finish the solution to this question H. It's very important to remember to solve this question the algorithm of the slow start and the congestion avoidance, and how we have the periods of TCP segments, okay, in this algorithm, how we have that the plots evolve, and so that we can represent it correctly. We remind the student that you can download the questions and the solutions, okay, of this problem as we keep solving this problem on the downloadable documents of this lecture. Hey everyone, on this lecture we are going to finish the solution to the problem 2 by solving the last question of this problem, which is the question I. The question I states, calculate the approximate duration of the period from the sketch in the previous question. So remember, on the question H we draw a sketch of the evolution of the TCP congestion window, and remember that this evolution of the congestion window is periodic. Okay, we have here different periods that follow the same behavior, and so we draw this sketch. And now what we need to calculate is the approximate value in seconds of this period. Remember that this period, the unit of the magnitude period is in seconds, okay? This is a unit of time. So we need here to estimate and give the value of this period. So first of all, what do we need? Well, the first thing we need in the first place to solve this question is to remember the assumption 4, where we were given the maximum segment size. The maximum segment size is 1500 bytes, which is the same as 1.5 kilobytes. So this is the value of one segment, okay? The maximum segment size is 1.5 kilobytes. And so if we study now the phase of the congestion avoidance that goes from this phase, okay, to this one, essentially, once we arrive the value of the congestion window divided by the maximum segment size, once this proportion arrives to the value of this low start threshold, then we go to the congestion avoidance phase. And so in the congestion avoidance phase, as we can see in here, it is important to know how many segments, how many units of the maximum segment size we have incremented, we have increased. So remember, the value of this low start threshold, we already calculated this on the question H, on the previous question. The value of this low start threshold is 25 kilobytes. And so we begin until we arrive to this value. Remember that this value is the maximum value of the window, which we also calculated. The maximum window, okay, the maximum value of the window is 50 kilobytes. Then we only need to calculate the difference to get the value in kilobytes that we have increased. Here it is very easy to see that 50 kilobytes, which is the value of the maximum window, minus, if we subtract the value of this low start threshold, 25, this gives us 25 also, right? 50 minus 25 is equal to 25. So this is the amount of bytes that the decongestion window increases in the congestion avoidance phase. But we don't want the value in bytes, we want the value in maximum segment sizes. Well, very simply, we can basically divide this increment, okay, this difference, the 25 kilobytes, we divide this by the value of a maximum segment size. And so we divide this difference, 25 kilobytes, and we divide by the maximum segment size. Remember that one maximum segment size is 1500 bytes. This is the same as 1.5 kilobytes. Since we have the numerator and the denominator in the same unit, we can simplify, and so now we have the value in segments. If we divide 25 by 1.5, this gives us 16.7. So 16.7 segments. And remember, and this is a fundamental notion about the slow start and congestion avoidance. Since in this sketch we have that the vertical axis, the y-axis, is the congestion window divided by the maximum segment size, this means that during the congestion avoidance phase, the congestion window is going to increase by approximately 1 segment for each round trip time. So, what consequence this gives us? Well, the conclusion is that approximately 16.7, okay, round trip times will have passed. So, as we know how many round trip times have passed, to calculate the period is trivial because we already know the value of one round trip time. What is the value of one round trip time? Well, we already saw in the question E that we here set the value of the round trip time to be 600 milliseconds, which is the same as 0.6 seconds. This is the value of one round trip time, 0.6 seconds. So, if the period is 16.7 round trip times, we only need to multiply 16.7 by the value of the round trip time, which is 0.6. And this gives us the value of 10. So the period on this sketch of the evolution of the congestion window is, as we can see here, 10 seconds. And this is the solution to the question I of this problem. Very well, so with this last question, we finish the solution to this problem too. Hey everyone, we are arriving to the end of the transport layer practical problems course. However, for those of you who are interested in continuing your path in computer networking, you can enroll to the Complete Computer Networks course, where we study all of the topics about computer networks and solve many problems not only about transport layer, but about all the areas in computer networking. You can check this course in the description of this lecture, as well as in my Udemy profile. My best regards and see you in the following course.